Which brings us to our last lecture, dealing with solid-state chemistry. Till now, we've talked about the elements, which could be handled as pure spheres, and the ionic compounds, and now we can consider answering questions about densities of ionic compounds. So we can ask questions, like what should the density of potassium bromide is? Well, first off, we're going to have to figure out what kind of crystal structure we'd expect potassium bromide to have. And that way you need to use our basic radius ratio. It's a 1-to-1 reaction. So we need to look up the size of the ions. One has to be a little bit careful when we're talking about the radius of the ions. Unlike the case where we were talking about the pure metals, do the X-ray crystal structure for a pure metal, and you can simply assume that half the distance between the two nuclei is, in fact, the radius of the two atoms that they're touching at that point. But the cations and anions are somewhat different. They're not identical, and so you can't just assume halfway between them is where the end's going to be. In the beginning, when they were first doing X-ray crystal structures, they sort of had to guess what radius they wanted to give each of the ions and tried to come up with a consistent set of data from that. As the technology improved, they were in fact able to get more than just the distance between the two nuclei. They could start getting the intensity of the electrons, rather the electron density around each center. And so if you do an X-ray crystal structure for something like sodium chloride, you see the electron density gives you a graph, like we see at the top. And from this you can tell where the center of the chloride is and the center of the sodium is. And so we can sort of assume that the low point in the curve of intensity is where they are touching. And so we can assign a radius to the chloride and the sodium with some idea of confidence. The textbook includes a couple pages where they give ionic radii. And one of the things you'll notice is that they aren't given one number. This is because, of course, there are several factors involved here. The atoms are not simply hard spheres. They are, in fact, clouds of electrons. The whole reason the cations and anions are coming together is because, in fact, they're attracted to each other. That means specifically the electrons are responding to each other. And so one of the things that makes a difference is how many other ions are, in fact, around each ion. And so if we look at potassium, we see several different radii. Not surprisingly, we notice that the bigger the hole the potassium ion is, the larger it appears to be. That's just what you'd expect. It's filling a bigger hole, and so its radius becomes somewhat variable. So we're just going to have to pick a radii. And other things being equal, we should probably pick the 6. 6 is one of the most common coordination spheres we see, and so we'll go with that one as our assumption. Another table gives us a radii for the bromide, and so we can try our calculation. Our 6th coordinate, potassium, would have a radius of 1.52 angstroms. The bromine, 1.82. That gives us a radius ratio of 8.35, which is way more than the 0.73 we figure is necessary to get us a cesium chloride structure. So we'd expect the structure for potassium bromide to be a cesium chloride structure. In the cesium chloride structure, the potassium would be in the center, the bromines would be at the corners of the long diagonal. The radius for an 8-coordinate potassium is 1.65 angstroms. The radius for our bromide, we said, was 1.82, so the long diagonal is 6.94 times 10 to the minus 8 centimeters. So the edge is the square root of 0.694 squared divided by 3. So the edge length is 4.0 times 10 to the minus 8 centimeters. So the volume of the unit cell would be 6.4 times 10 to the 23rd, 10 minus 23rd cubic centimeters. So 119 grams per mole of potassium bromide. There are 6.022 times 10 to the 23rd formula units in a mole of potassium bromide. There's 1 formula unit per unit cell. The unit cell has a volume of 6.4 times 10 to the minus 23 centimeters. So our theoretical value for the density of bromine is 3.09 grams. The actual density, 2.75 grams per cubic centimeter, is off by about 10%. So we're getting basically 2 significant figures in our calculation, which actually isn't too bad considering all the assumptions and all the approximations we made in trying to create our calculation. We can now consider the structure for ionic compounds with the formula AX2, that is where you have twice as many of one of the ions as the other ion due to the charges. Where the ions are approximately the same size, we get what is known as the calcium fluoride structure. In this structure, the ions that we have fewer of form a face-centered cubic structure, and the ions we have more of fit into that structure, filling all the tetrahedral holes. This gets us our 2-to-1 stoichiometry. Each of the black ions is in the center of a simple cube, and each of the yellow ions is in the center of a tetrahedron hole. Where one of the ions happens to be considerably larger than the other one, we get what is known as a cadmium iodide structure. In this structure, the more numerous ion simply forms a hexagonal closest packed array, and within that closest packed array, filling the tetrahedral holes, we have a layer of the other ion. The difference is, in this case, is that the other ion occupies only every other layer. That is, you have one layer of iodide, a layer of cadmium, another layer of iodide, then another layer of iodide, before we get to another layer of cadmium. And finally, where one ion is vastly larger than the other ion, we get what is known as a rutile structure for like titanium oxide. In the rutile case, as you can see, each of the white ions ends up in the center of a triangle of the blue ions, and each of the blue ions ends up occupying an octahedral hole of white ions. And that brings us to the end of our discussion of solid-state structures for the elements and for simple ionic compounds. The next chapter we're going to get started on is coordination chemistry, my personal favorite in inorganic chemistry.